Welcome. In this video we're going to implement the Self-Normalizing Neural Network paper. So the paper that introduced the SELU activation function, so a great paper from 2017. We will reproduce the figure 1 from the paper. So basically this figure where they compare a neural network with batch normalization and with ReLU with a standard neural network with the SELU activation function, what they call Self-Normalizing Neural Network. So we'll reproduce this figure. These are the results we'll get by the end of this video. So we are pretty close to the figure presented in the paper. I will put the link of this implementation in the comment. If you use the implementation or if you find it useful, please leave a star so that it gives visibility to the repository and so that other people can discover it. Also leave a thumbs up to this video and also subscribe for more content related to machine learning. That being said, let's dive directly into the implementation. So we are going to implement the SELU activation function that is described by this equation. We will come back to that in a moment. So we are going to use PyTorch to implement our the paper. We use other packages such as NumPy to play with the data, Seaborn on Matplotlib to plot the results, TQDM to see a training progress on other components such as Keras to load the data, on skitlearn to normalize the data. But let's dive directly to the implementation. So first we can use Keras to load the MNIST data. So we can use the load data function to load the training on testing data. We can use the standard scaler from skitlearn to normalize the data, and so that they are nicely scaled or nicely processed to be fed to the neural network. Now we can directly move on to implementing the SELU activation function. So we have two main parameters, alpha and lambda. So they can be seen in this equation 2, lambda and alpha. These are the standard values used for those parameters. So we can just store them in the constructor, and then we can implement the forward parse. And we are just doing a straightforward implementation of the equation from the paper. There was different ways to implement this. We could have used a mask to compute where x was greater than 0. There are a lot of ways to implement that. The one I've chosen, which is also the one that is used, for example, in the initial implementation from the authors, when x is greater than 0, we need to use we need to put 0. So when x is greater than 0, we just return lambda times x. So that means that if x is greater than 0, we return 0, otherwise we return 0. And if x is, so basically we are implementing this part. And if x is lower or equal than 0, that means we are implementing this part. So we have alpha times torch.x minus 1. So basically it's a way to implement, it's like a trick to implement this equation by using the maximum and minimum function. You can do the maths, just take a sheet of paper and think about it, but it's just a standard implementation of the equation. It could have been implemented other ways, for example, like with a mask, and maybe it would have been a bit easier to understand, but it's still pretty easy to grasp. Once we've implemented the SELU activation function, we can build a neural network out of it. So basically we can build a SNN self-normalizing neural network by just creating an MLP with a SELU activation function in between layers. And because we want to do classification, we use a lock softmax at the very end of the neural network. Then we can just implement the forward parse as it's needed by PyTorch, and we just feed the input x to our neural network. We can do the same for MLP. So we can create an MLP with ReLU activation function and with batch normalization, so that we can compare this model, the MLP, to the SNN model introduced in the paper. Again, we implement the forward function by just feeding the input to the neural network. Once this is done, we can implement a training function. So we take as input the model. We take as input an optimizer to update the weights of the model. We take a dataset, the loss function, the negative log likelihood loss because we want to do classification, a device on which we want to train. Obviously, we prefer to train on GPU when it's possible, on the number of epochs we want to train. So then we can iterate over a number of epochs. During each epoch, we'll iterate batch per batch over the dataset. And then in each batch, we'll extract the input, so the image, on Y the target, so the label. We'll compute the log probability of the model for each class. And then we will compute the loss, so we'll use the negative log likelihood loss to compare the log probabilities predicted by the model to the target class, and we want to maximize the probability of the target class. Once this is done, we can start the backward pass to compute the gradient and call optimizer.step to update the weights of the model with respect to the gradients. Then we can compute the training loss and return it. Now we can obviously when you work with neural networks, the initial initialization of the weights is very important. So we can create an init function to initialize the weights of the neural network. So basically, when we have nn.linear, so when we have a linear layer, so wx plus b, we will initialize the weights, so the matrix w with a normal distribution with a mean of 0 on the variance that is equal to some gain divided by the number of hidden units. So by default, the init gain is equal to 1. It's called the Xavier initialization, and we set the bias to 0. So we use a gain of 1 for SELU, so for self-normalizing neural networks, but for ReLU, so for the MLP, we want to use a gain of 2. This is the E initialization, and it was shown that it works better when you use a ReLU to have a gain of 2. So now we can put everything together. We can create, we can define the device on which we want to train, the number of epoch on the dataset. So we'll use the, we just iterate over the dataset. We fetch the training, we create tuple of input on target, and we put everything in a data loader, in a PyTorch data loader. Then we can start with the CNN. So we will log the training loss for the self-normalizing neural network. In the paper, they show different curves with depth of 8, 16, and 32. We can do the same for the MLP. So the only difference between those two block of codes is the neural network we are using. We use the same optimizer with the same learning rate, and we call the same training function. Once we have launched training and we've got those training loss, we can plot them. So now we're just calling matplotlib, using different colors for each curve, using different labels on doing the showing the figure. On this should give you those results. So yeah, we see that for CNN, the deeper the network, the better the results, at least the training loss. While for MLP, it's not the case, and it's also noisier. So I really hope you liked this video and that it was helpful to you. If it was, please leave a thumbs up and also subscribe for more content related to machine learning. Thank you.